Hi, my name is Aiden Haggerty, and today my tutorial is going to be on Module 11. And more specifically, we are going to expand upon what we learned about solubility from Module 11, and we are going to learn about the solubility of a gas in water. So if we look back at our solubility lectures, we learned about the basics of solutions. We learned about solutes, solvents, and precipitates, and most typically our solutes were solid state matter. And we also learned about the KSP, which is a solubility product. We learned about Q for solubility, which is the ion product. And those two terms helped us determine precipitates in solutions. We learned that if Q was greater than KSP, a precipitate should occur. If Q was equal to KSP, then the solution was just saturated and no precipitate would occur. And we also learned that when Q was less than KSP, then a precipitate could not occur. We also learned about the pH and pOH of solutions. We learned about how to find molar concentrations in solutions, and we connected all of what we learned back to the equilibrium idea. And so today we're going to be learning about the basics of gas solubility in water. And so gas solubility is based upon the chemical structure of the solute and the solvent in solution. And so since water is going to be our solvent here, the solubility of the gas is going to depend on the gas's ability to make electrostatic interactions with the water molecules. And so more generally, we can break this down into the fact that gas solubility is based upon a gas's ability to make dipole interactions or the gas's lack thereof ability to do that. And so gases which can make dipole-dipole interactions are typically going to have greater solubilities than the gases that can't. And this holds true unless the gas is being dissolved into a liquid which cannot make dipole-dipole interactions. And this is rare, however, in this case, the gas that can't make dipole-dipole interactions is going to have a greater solubility. And so this all kind of boils down into what we call like dissolves like. Polar solutes dissolve in polar solvents, and nonpolar solutes dissolve in nonpolar solvents. And so this also tells us that polar solutes can't dissolve into nonpolar solvents, and the same is true for nonpolar solutes. They can't dissolve into nonpolar solvents. And so now that we understand how gas structure can affect gas solubility, we can look into more factors that also go into the solubility of a gas. And so the solubility of a gas is also going to be determined here by the partial pressure of the gas being dissolved into water. And so we can see this makes sense. As the pressure of the gas increases, the solubility is also going to increase. Because when more and more pressure are applied to the gas and the water at the same time, the gas is more likely to be forced into the water. And by forced into, I mean dissolve into the water. And we can see this in the picture on the left right here. As pressure is increased, more gas molecules are soluble at a higher pressure. And so this relationship between the pressure of the gas and the solubility can be written out mathematically in what we call Henry's law. And so Henry's law is written here as Cg equals K times Pg. And so what this boils down to is that C is the concentration of gas, P is the partial pressure of the gas, and K is the proportionality constant. And this has many names. It can be called the Henry's constant. It has a lot of different names within the chemistry community. And so K depends on the solute and solvent identities and the temperature of the solution as well. And so there's some things that we need to note with Henry's law, and we'll look at those on the next slide. And so a couple things for us to remember for Henry's law is that Henry's law works at a constant temperature, because at very high temperatures, at least for water we know here, is that at high temperatures, water boils, becomes a gas itself. And so dissolving a gas into a gas is not the same as dissolving a gas into liquid water. And so Henry's law also works when the solution is in equilibrium and there are the same molecules throughout the solution. Henry's law doesn't apply when the gas is under extreme pressure, and this is because typically insoluble gases can become very, very soluble at extreme pressures, and by extreme pressures, I mean very extreme pressures. And Henry's law also doesn't apply when there's a chemical reaction between the solute and the solvent, and in this case, it's going to be our gas and water. And so there's an example here when ammonia gas is dissolved into water, the solubility of ammonia doesn't increase with pressure, as we would expect with Henry's law, because the ammonia is reacting with the water and taking an H plus from the H2O. So before we move on to a practice problem for gas solubility using Henry's law, we're going to look at two real-life examples of gas solubility. The first example is something that a lot of people see in their everyday lives, and this is carbonated drinks. The most obvious of carbonated drinks, of course, is soda. It also includes seltzer water and energy drinks. And these are a modern triumph of gas solubility. It's $1 billion market, and this is all because of carbonation. And so the carbonation in these drinks is made through immediately before packaging. The can or the bottle before it's sealed off is going to have carbon dioxide shot into the liquid that is in the can or the bottle. And this creates carbonation. The carbon dioxide is dissolved into the liquid, and that gives us those little bubbles. And so obviously more carbon dioxide is going to be shot into the can or the bottle before sealing than the liquid can hold. And this gives us the excess carbon dioxide that sits in the bottle until you open it up. You crack your can or you unscrew your bottle and you get that snapping sound. That's that extra carbon dioxide being released from the bottle. Interestingly enough, though, not all carbonated drinks are made by intentionally adding carbon dioxide. Now, carbon dioxide is a byproduct of fermentation, so this means that a lot of alcoholic drinks become carbonated just through the process of being made. The fermentation of alcohol creates the carbon dioxide, which gives the liquid carbonation. And fun fact, interestingly enough, scientists recently found that there are taste buds on the tongue that do taste for carbonation as well. Now we're going to move on to a more serious example of gas solubility in real life. And so what you're looking at here is Lake Nyos in Cameroon. And Lake Nyos is important because in 1986, a limnic eruption occurred at Lake Nyos. And a limnic eruption is when volcanic activity beneath the lake caused massive amounts of carbon dioxide to be released into the lake water. And this saturated the water at the bottom of the Lake Nyos with carbon dioxide. And so this combined with lake turnover, which is a natural phenomenon, caused the water at the bottom of the lake to be switched around and become the water at the top of the lake. And this was disastrous, as the water that was saturated with carbon dioxide then created a large carbon dioxide cloud. And this cloud traveled down into the valley below the lake and killed 1,746 people and injured many more in the process. And this disastrous natural phenomenon led many scientists to go to Lake Nyos in order to try and solve the problem. And solve the problem they did. The scientists that went to Lake Nyos realized that the carbon dioxide within the lake could also be the key to making the lake safe. And so what these scientists did is that over years of research and study at Lake Nyos, they created self-sustaining carbon dioxide pumps, which they then installed into the lake. And so what these self-sustaining carbon dioxide pumps did was they took carbon dioxide saturated water from the bottom of the lake, like what happened during the disaster, and they let out small amounts of this carbon dioxide saturated water from the lake at a time. And this assures that a large cloud that contains enough carbon dioxide to harm humans could never come out of the lake again, as carbon dioxide was being steadily removed from the lake in small intervals. And so by 2019, these pumps had actually successfully removed all of the hazardous carbon dioxide from Lake Nyos, and people had once again began to move into the valley below the lake.